In the previous activities, you explored the lower layers of the OSI model: the physical layer, the data link layer, the network layer, with IP addressing, routing tables, and subnetting, and you practiced with network address translation and domain name system resolution. You now have a solid foundation to climb higher in the model and understand how applications communicate over a network. This lesson covers OSI layers 4 through 7, with a deep focus on the Hypertext Transfer Protocol, which is the backbone of web communications and one of the most critical surfaces in cybersecurity and web application penetration testing. The Transport Layer, Layer 4. Layer 4 is the transport layer. You already know the two main protocols at this level from the quiz on subnetting, routing, and TCP/UDP, the Transmission Control Protocol and the User Datagram Protocol. Let's consolidate and deepen this knowledge. The transport layer is responsible for end-to-end communication between two processes running on different machines, while the network layer, Layer 3, handles routing between machines using IP addresses. The transport layer adds the concept of ports to distinguish between multiple simultaneous communications on the same machine. A port is a 16-bit number, ranging from 0 to 65,535, that identifies a specific process or service on a host. For example, when your browser and an SSH client are both running on your machine at the same time, both may be sending and receiving data. The transport layer uses port numbers to ensure that the data for the browser goes to the browser process and the data for the SSH client goes to the SSH process. Ports are split into three ranges. Well-known ports: 0 to 1023, reserved for standard services like port 80 for HTTP, port 443 for HTTPS, port 22 for SSH, port 53 for DNS over UDP registered ports, 1024 to 49151, used by applications like databases. Dynamic or ephemeral ports, 49,152 to 65,535, assigned temporarily by the operating system to client-side connections. The Transmission Control Protocol, TCP, is a connection-oriented protocol. Before any data is exchanged, TCP establishes a connection through a three-way handshake. 1. The client sends a SYN, synchronize, segment to the server. 2. The server responds with a SYN ACK, synchronize acknowledge, segment. The client sends an ACK, acknowledge, segment back. Only after this handshake is complete can data flow. TCP also guarantees delivery. If a packet is lost, it is retransmitted. It also guarantees ordering. Data arrives in the correct sequence even if packets arrived out of order. This makes TCP ideal for protocols like HTTP, HTTPS, and SSH where data integrity matters. The User Datagram Protocol, UDP, is connectionless and does not guarantee delivery or ordering. There is no handshake, no retransmission, and no acknowledgement. This makes UDP faster and lighter, ideal for real-time applications like video streaming, online gaming, or the domain name system where a quick response matters more than guaranteed delivery. From a security perspective, Layer 4 is critical. Port scanning tools like Nmap operate at this layer to discover which ports are open on a target machine, which helps identify running services and potential attack surfaces. The Session Layer, Layer 5. Layer 5 is the session layer. Its role is to establish, maintain, and terminate sessions, dialogues, between two applications. A session is a logical connection that persists over time beyond a single request or packet exchange. In practice, many modern protocols do not implement the session layer as a clearly separate component. The functionalities of Layer 5 are often handled within application protocols themselves. For example, in web browsing, session management is often done through cookies or tokens at the application level rather than a dedicated session protocol. However, understanding the concept is important in cybersecurity because session hijacking attacks exploit weaknesses in how sessions are established and managed. If a session token, a piece of data used to identify an authenticated user, is stolen or predicted, an attacker can impersonate the legitimate user without needing their password. The Presentation Layer, Layer 6. Layer 6 is the presentation layer. It is responsible for data formatting, encoding, encryption, and compression. Its role is to ensure that data sent by one application can be understood by the receiving application, regardless of how the two systems internally represent data. Concrete functions of Layer 6 include character encoding, converting text from one encoding to another, for example, from ASCII to Unicode/UTF-8, data serialization, transforming data structures into formats like JSON, JavaScript object notation, or XML, extensible markup language, for transmission. Encryption and decryption, TLS, transport layer security, which secures HTTPS connections, is often associated with this layer. Compression, reducing data size before transmission. In the context of web security, the presentation layer matters because encoding mismatches or unexpected data formats can lead to vulnerabilities. For example, an attacker might encode a malicious payload using base64 or URL encoding to bypass input validation filters that only check for plain text patterns. The application layer, Layer 7. Layer 7 is the application layer. This is the highest layer of the OSI model and the one closest to the end user. It defines the protocols that applications use to communicate over the network. This layer does not refer to the application software itself, like your browser, but to the communication protocols that those applications use. Examples of Layer 7 protocols: HTTP and HTTPS, used by web browsers and web servers. DNS, used for name resolution, which you already studied. SMTP, Simple Mail Transfer Protocol, used to send emails. FTP, File Transfer Protocol, used to transfer files. SSH, Secure Shell, used for secure remote command line access. Layer 7 is the primary target in web application penetration testing, because this is where application logic lives: authentication, authorization, data input, sessions, and business logic. The vast majority of vulnerabilities listed in the OWASP Top 10, Open Web Application Security Project, are Layer 7 vulnerabilities. Deep Focus, the Hypertext Transfer Protocol, HTTP. HTTP is the foundation of data communication on the World Wide Web. It is a Layer 7 protocol that defines how web clients, typically browsers, and web servers exchange information. Understanding HTTP in depth is non-negotiable for anyone working in web security or DevSecOps. HTTP is a request-response protocol. The client sends an HTTP request, and the server sends back an HTTP response. By default, HTTP operates over TCP port 80. HTTPS, HTTP Secure, is HTTP with TLS encryption on top, operating over TCP port 443. HTTP requests. An HTTP request has a precise structure. It is composed of 1. A request line. This contains the HTTP method, the target resource path, and the HTTP version. 2. Headers, key value pairs that provide metadata about the request. An optional body, data sent by the client to the server, used in POST and PUT requests, for example. Example of a raw HTTP request: get/index.html http/1.1. Host, www.example.com. User agent, Mozilla/5.0. Accept, text/html. Connection, keep alive. In this example, get is the HTTP method. /index.html is the path of the requested resource. HTTP/1.1 is the protocol version. Host, user agent, accept, and connection are headers. HTTP methods. HTTP defines several methods, also called verbs, each with a specific semantic purpose. Get, retrieves a resource. No body is sent. Should not modify server state. Example, loading a web page. Post, sends data to the server to create or process a resource. Body contains the data. Example, submitting a login form. Put, sends data to replace an existing resource entirely. Example, updating a user profile. Patch, partially updates an existing resource. Delete, deletes a specified resource. Head, like get, but only retrieves headers, not the body. Useful for checking if a resource exists. Options, asks the server which methods are supported for a given resource. Important in cross-origin resource sharing, CORS, security checks. From a security standpoint, misconfigured servers that allow PU delete methods on unprotected endpoints can be exploited by attackers to upload malicious files or destroy data. HTTP responses. An HTTP response also has a structured format. 1. A status line, HTTP version, status code, and a reason phrase. 2. Headers, metadata about the response. 3. An optional body, the content returned, HTML page, JSON data, image, etc. Example of a raw HTTP response. HTTP/1.1200 OK. Content type, text/HTML, charset equals UTF-8. Content length, 1234. Set cookie, session_8 equals AB123, HTTP only, secure. HTML</HTML. HTTP status codes. Status codes are three-digit numbers grouped by category. 1XX, informational. The request was received and is being processed. Example, 100 continue. 2XX, success. The request was received, understood, and fulfilled. Example, 200 OK. Success, 201 created, resource created after a post request. 3XX, redirection. Further action is needed. Example, 301 moved permanently. The resource has a new permanent URL. 302 found, temporary redirect. 4XX, client errors. The request contains an error. Example, 400 bad request, malformed request. 401 unauthorized, authentication required. 403 forbidden, access denied. 404 not found, resource does not exist. 5XX, server errors. The server failed to fulfill a valid request. Example, 500 internal server error. 502 bad gateway. 503 service unavailable. In penetration testing, status codes reveal a lot of information. A 403 response on a directory confirms the directory exists even if access is denied. A 500 response often indicates that user input was not handled correctly, which may indicate a vulnerability. HTTP headers in detail. HTTP headers carry critical information and are a major attack and defense surface in web security. Common request headers. Host specifies the domain name of the server. Mandatory and HTTP/1.1. Virtual hosting relies on this header to serve different websites from the same IP address. Cookie sends stored cookies to the server. Sessions are often maintained through session cookies. Authorization carries credentials, for example in basic authentication, base64 encoded username and password, or bearer tokens, JSON web tokens. Content type tells the server the format of the body being sent, for example, application/JSON, application/XWWW form URL encoded, multipart/form data. User agent identifies the client software, can be spoofed by attackers. Referrer, note, historically misspelled, indicates the URL of the page that led to the current request. Common response headers with security implications. Set cookie instructs the browser to store a cookie. Security attributes matter. HTTP only prevents JavaScript from accessing the cookie, mitigating cross-site scripting attacks that try to steal session cookies. Secure cookie is only sent over HTTPS connections. Same site controls cross-origin cookie sending, mitigating cross-site request forgery attacks. Content security policy defines which sources of content, scripts, images, styles are trusted. Helps prevent cross-site scripting. X-frame options prevents the page from being embedded in an iframe, mitigating clickjacking attacks. Strict transport security forces the browser to only use HTTPS for future connections to the domain. Access control allow origin controls which external domains can make cross-origin requests, cross-origin resource sharing mechanism. HTTP versions. HTTP/1.1 is the most widely deployed version and uses persistent connections by default. The TCP connection stays open for multiple requests. HTTP/2 introduced multiplexing, multiple requests over a single connection simultaneously, and header compression, improving performance. HTTP/3 uses QUIC, a UDP-based protocol, instead of TCP, further reducing latency. From a security perspective, HTTP/2 and HTTP/3 can affect how security tools intercept and analyze traffic, which is relevant when using a proxy tool like Burp Suite during a penetration test. Cookies and session management. Cookies are small pieces of data stored in the browser and sent automatically with each HTTP request to the matching domain. They are primarily used for session management. After a user logs in, the server creates a session and sends back a session identifier via a set cookie header. The browser then sends this cookie with every subsequent request, allowing the server to recognize the authenticated user without asking for credentials again. Poor session management is one of the most common web vulnerabilities. Predictable session identifiers allow attackers to guess valid sessions. Session tokens transmitted over HTTP, not HTTPS, can be intercepted by an attacker on the network. This is exactly the kind of attack where understanding both Layer 2 sniffing and Layer 7 protocols together is powerful. Failure to invalidate sessions on logout means a stolen token remains valid indefinitely. HTTP authentication. HTTP supports several authentication mechanisms. Basic authentication. The client sends the username and password encoded in base64 in the authorization header. This is not encryption. base64 is trivially reversible. Basic authentication must always be used over HTTPS. Digest authentication, a challenge response mechanism that hashes credentials before sending them, slightly more secure than basic authentication. Token-based authentication. The client sends a token, often a JSON Web Token, in the authorization header after initial login. JSON Web Tokens are base64 encoded signed structures containing claims about the user. OAuth 2.0 and OpenID Connect, widely used delegation and authentication frameworks used by services like Google or GitHub. Common HTTP-level vulnerabilities overview. While the detailed exploitation of these vulnerabilities will be covered in dedicated chapters, it is essential to understand them in the context of HTTP. SQL injection through HTTP parameters. Attacker sends malicious input in a GET parameter or POST body field that is directly inserted into a database query without sanitization. Example: the URL/search query equals OR1 equals 1 could return all records from a database if the query is not parameterized. Cross-site scripting, XSS. Attacker injects malicious JavaScript into a response that is then executed in the victim's browser. Stored XSS is injected into the database. Reflected XSS is echoed directly from a URL parameter. Cross-site request forgery, CSRF. An attacker tricks an authenticated user's browser into sending an unwanted HTTP request to a trusted site. The same site cookie attribute and anti-CSRF tokens are the main defenses. Insecure direct object reference. An attacker modifies a parameter, like an identifier in a URL, to access resources belonging to another user. Example: changing /account ed equals 123 to /account ed equals 124 to access another user's account. HTTP response splitting and header injection. Attacker injects new line characters into HTTP response headers to manipulate the response seen by a proxy or browser. Conclusion. Layers 4 through 7 of the OSI model form the complete communication stack that makes application-level networking possible. Layer 4 provides reliable, TCP, or fast, UDP, transport between processes using port numbers. Layer 5 manages sessions. Layer 6 handles encoding and encryption. Layer 7 is where application protocols like HTTP live and where most web security challenges occur. HTTP, as the dominant protocol of the web, is your primary working surface as a cybersecurity specialist and penetration tester. Mastering its structure, methods, headers, status codes, cookies, and authentication mechanisms gives you the vocabulary and technical understanding needed to identify, exploit, and remediate web vulnerabilities. Every tool you will use in web penetration testing, from Burp Suite to custom Python scripts, operates by sending, intercepting, or modifying HTTP requests and responses.